When we use energy conservation to solve a problem, we would love to say that the mechanical energy in our system never changes. But we know that's not always the case. An example we always use with energy conservation is money. And if we have a classroom filled with people and we lock the doors, the amount of money in the room is fixed. It might get transferred from one person to another. Maybe we'll have a big rumble, big fight, and the money gets transferred. Some people might leave with more money than they came in with, some less, but the total money is fixed. That's true if the doors are locked. We know the amount of money in the room is fixed. But if we allow people to enter and leave through those doors, then the amount of money in the room is always changing, and we have to account for that. We have to keep track of how much money leaves with people when they leave the room and how much money comes in. It's the same with energy. If a force crosses over our system boundary and does work on our system, it's going to change the mechanical energy in our system. So we have to be able to account for that. Well, we can add another term here. If this force reaching into our system does work on our system, it will increase the energy of the system. So if we look at this equality, we're going to end up with more energy than we started with. So we would have to add something to the left side of this equation to keep that equality if there's external work adding energy to our system. And if that external force removes energy from our system, then we're going to end up with less. So we have to subtract something from the left side of that equation to keep that equality. We write it like this: the initial energy plus the work done by external forces is equal to the final energy. If the work done by external forces is positive, the external force is doing work on our system, increasing the energy of the system. So we have to add a positive number to the left side of this equation to keep the balance, because we're going to end up with more mechanical energy in our system than we started with. We've added some. If the work done by the external force is negative, it's removing energy from our system. So we're going to end up with less. So we put a negative number on the left side of our equation to balance this and keep that equality. Now we also know there's one more thing that could change our mechanical energy. If I give a box a push and it starts sliding across the floor, what happens to it? Eventually it comes to rest because of friction with the ground. Friction is going to change our mechanical energy. It's going to transform some of that mechanical energy into heat. The surfaces are going to heat up a little bit. But we can account for the work done by friction. We either have to subtract something from the left side of our equation or add something to the right side of our equation, because we know we're going to end up with less mechanical energy at the end than we started with because of friction. So we subtract something from the left side of our equation or add something to the right side of our equation. We usually write it like this. The initial energy plus the work done by friction plus the work done by external forces is equal to our final mechanical energy. Why did I write it as plus W friction on the left side of my equation? Didn't I say we had to subtract something from the left side to keep that equality? Well, the work done by friction is always negative. In plugging in the proper value for the work done by friction, we'll put a negative number in there and subtract something from our initial mechanical energy to end up with our final mechanical energy. And what do I mean by mechanical energy? Well, in physics 4a, we know about three kinds. We know about kinetic energy, we know about gravitational potential energy, and spring potential energy. So anytime you see mechanical energy, this E, it means it's going to be any one or all three of these: kinetic energy, gravitational potential, or spring potential energy. So I have work done by external forces here. That means we need to know if something is an external force. Is it reaching into our system, doing work on the system? Or is it already in our system? We need to know if it's an external force or not. We need to define a system boundary and understand what's inside of our system and what isn't, what's reaching across that boundary and what isn't. That's where interaction diagrams come in handy. Here's a problem we want to solve using energy conservation. A box is connected to a spring. We pull on the box with a constant force, F pull, for a distance d. There's friction. If the box starts from rest at the equilibrium position of the spring, how fast is it going after the distance d? Let's write out our energy equation. Initial mechanical energy plus the work done by friction plus the work done by external forces is equal to our final mechanical energy. We have to know what's in our system and what isn't. What is mechanical energy? Well, it's kinetic energy, gravitational potential, and spring potential energy. So I could have kinetic energy at the initial point in my problem, gravitational potential energy, and spring potential energy. And at the end of my problem, I could have the same three forms of mechanical energy. You can see now it's important to understand what's in our system. If we are defining the system such that it includes the Earth, we would have gravitational potential energy to account for changes of energy in the Earth mass system. And we would not have an external force from gravity reaching in, because gravity would be in our system. It would not be crossing the system boundary. But if we exclude the Earth from our system, then we will not have gravitational potential energy. That's how we account for exchanges of energy within our system. We would have an external force because the force of gravity would be crossing our system boundary, reaching in, doing work on our mass. The same would be true with springs. If we include the spring in our system, we can account for exchanges of energy with the spring through this potential energy term. And we would not have an external force from the spring reaching into our system. But if we exclude the spring from our system, we can't have spring potential energy. How would we account for the spring's effect on our system? We would say it reaches in as an external force and does work on our system. We account for it that way. So let's talk a little bit about how we define our system. We're going to use an interaction diagram to help us figure out what's in our system and what isn't. When we draw an interaction diagram, we want to indicate every item that's important in our problem. So I'll put a bubble here and fill in spring. I've got the mass. I've got a hand or something pulling on the mass. And I've got the Earth. When I draw these, I try to draw them in the relative orientation they are in the problem. Here I've got a spring followed by a mass followed by a pulling force. And here I'm drawing my spring followed by my mass followed by my hand, which is pulling on everything. Now we'll draw in our interactions. What are interactions? Forces. Forces are the result of interactions between two objects. The spring and the mass are exerting forces on each other. They are interacting with each other. The hand and the mass are interacting with each other. They are exerting forces on each other. The Earth is interacting with the mass several ways, right? We have a gravitational force from the Earth on the mass, but we also have this surface that's interacting. And we say surfaces can interact two ways, through a normal force and through a friction force. So I like to draw the surface interaction as a double arrow. One side represents the normal force, one side represents the friction force. So just to recap, this one is from the surface. We've got a normal force and a friction force. This one is gravity, and I'll write F sub g there. This one is our pulling force, and this one is our spring force. So those arrows, those double-sided arrows, represent an interaction. The mass is exerting a force on the spring is exerting a force on the mass. The Earth is exerting a force on the mass through gravity, and the mass is exerting a force on the Earth through gravity. So these double-headed arrows. Now we want to define our system. My rule of thumb is you want to include as much in the system as possible because you want to use potential energy terms. If we include the Earth, if we include springs, we can use potential energy to describe those interactions. So we want to include those things. And my rule of thumb is if we just have a hand reaching in doing something, or one end of a rope, and we don't know what's going on with the other end, then I make those external forces that reach across the system boundary. So if I look at this problem, I would immediately draw my system boundary to be something like this. You can see we have a hand reaching in across that boundary doing work. That's our external force, reaching in, crossing the boundary. But these other three forces here are within our system. They are internal forces, and we would account for their interactions using potential energy terms. So let's take this energy equation and fill it in the way we would to solve this problem using this system definition. And then in the next video, we'll do other system definitions, and you'll see how the energy equation changes when we do those. So now I can look at this equation and immediately check off the ones that are zero. For example, at the beginning of my problem, the box is not moving. It starts from rest. So this would have to be zero. Kinetic energy initial would have to be zero. At the end, the box is moving. So I'm going to need that final kinetic energy term. My object never goes up or down. It never changes altitude. It's always at the same height. So whatever gravitational energy I have at the beginning, I'm going to have the same amount at the end. So I don't need this term. I could basically define this as my zero height, and I have no gravitational energy at the beginning or the end. At the beginning of the problem, my spring is not stretched or compressed. It's at its equilibrium position. If it's at its equilibrium position, it's not storing any energy. This is zero. At the end, it is stretched. So I'm going to need a term U spring final to account for the energy in the spring at the end of my problem. And I'm going to have work done by friction, and I'm going to have work done by an external force because I've got a hand reaching into my system doing work. So let's write out each of these terms. Work done by friction is going to be the force of friction times the distance times the cosine of 180 degrees. That's where our minus sign comes from. Work done by the external force is going to be the external force, F pull, times the distance times the cosine of 0 degrees, right? We're pulling in the same direction. And that has to equal 1/2 m v final squared 1/2 kx squared, where x is the amount the spring is stretched or compressed. But we know what that is, don't we? That's the distance we move, d. Capital D, the amount the spring stretched. And now the only unknown is v final. We plug in all the numbers we know, and we can solve for v final.